one remark about Fokker. Maybe one of you guys can, you PhD students or you, something about the Fokker board I heard?
So you said he is going to buy the softball this afternoon. So this student who emailed him about softball to start to organize a sonogram.
The other remark is there's a typo in the program, in the detailed program about lecture on Wednesday. The third lecture on Wednesday is at 2:15 p.m., not 2:30. It's correct in the small program, the detailed program, there's a typo. So only note that Wednesday after lunch we start at 2:15. Okay, now let's come to the last lecture of the day. So it's Steve Teitel who will introduce us to simplified Granular systems in Germany.
So I'd like to thank you. Do I need a microphone or?
Yes.
Yes. Yes. Is this on? Is that okay?
So you have to turn it on.
It's not on. It says it's on. Is that better?
Yeah.
Is that okay? Okay. So first I'd like to thank the organizers for inviting me to speak at this summer school. This is the first time I've given lectures at a summer school, and so not knowing quite what to do, we had some talks today that were just nice PowerPoint presentations and some which were on the blackboard, so I will try to do both. I'll give you a nice multimedia presentation. So I'm going to try to tell you a little bit about granular materials. And because of the prestige of this summer school, you deserve, of course, to have an expert telling you about granular materials. And so I have to confess right off, I'm not at all an expert in granular materials. This is just a subject that I have been working in fairly recently. But I find it a very exciting and interesting one. And so, of course, giving lectures about something is one of the best ways to learn about it. And so, in the course of preparing these lectures, I've learned a great deal about granular materials, some of it even just last night. But I will try to, so also I should say, this talk on granular materials is not meant to be any sort of comprehensive survey or anything like that. It's just my take on things as interesting things came in my path, and I hope you will also find it interesting. But if there are more experts in the audience, and I think there's at least one, I apologize, and for all those of you out there in the world at large who might stumble on this on the internet and might be a real expert, I have to certainly apologize for any errors or omissions that might come up in my talks. Okay, so let me first just sketch very quickly what the three lectures will be about. Today's talk will be just a quick, an informal sort of introduction. It's the last talk. I'm tired. There won't be anything too terribly technical. Lecture 2. Start doing some statistical mechanics and talk about ensembles for static jammed states. Even though granular material is not in equilibrium, we're nevertheless going to try and describe some of its properties using methods familiar from statistical mechanics. So everything today and tomorrow is all static. Many non-equilibrium things are non-equilibrium because they are changing in time. But in the first two lectures, nothing at all is going to be changing in time. But the third lecture have a little motion. I'll talk to you about what's really my own work in this area, which has to do with shear-driven granular materials, and discuss what's called jamming phase diagram. Okay. So, granular materials have some key properties that, well, I'll just list them. So one, the interaction of the particles of granular material is about as simple as it can get. The particles will only interact when they touch each other. When they don't touch, they don't know they're around. We can think of two types of particles. One we can call hardcore particles, which are incompressible. Okay, so when they meet, they don't squeeze into each other at all. They just take up volume that another particle can't occupy. And then a lot of what I'll talk about is softcore. These are particles which are deformable. As they contact, they can push into each other, and then they feel some repulsive force pushing them away from each other. Okay. The other thing about granular materials is that the particles are generally taken to be very large, okay? Meaning masses of, well, big, okay? In particular, they're large, and so we can ignore thermal fluctuations altogether. The energy in thermal fluctuations compared to any kinetic or other energy, mass energy of these grains is zero. So even though we might be at room temperature doing our experiment, as far as the granular material is concerned, we're at zero temperature. And the last thing I want to point out is that when granular particles collide, and generally the collisions are inelastic and energy is dissipated. So if you were to somehow pump energy into your granular particle system, and all the particles are jiggling around, whatever, and then you turn off the input of energy, the particles will just settle down into some static position and cease to move any further, because the energy is dissipated in the collisions. There's some coefficient of restitution, or whatever model you like for dissipating the energy. Okay, so these features, in particular these two, mean that our granular materials are not equilibrium systems. They are not in thermal equilibrium because T is zero. They're not, the various configurations that are allowed are not determined by any thermal Gibbs ensemble. Okay, nevertheless, we want to try and understand some things about them using methods of statistical mechanics. Okay. So, we can imagine as my granular material a set of n particles. And we can imagine each of those particles has a volume V0. And for now, I can say all the particles are identical. They don't have to be. And let's say we put those particles inside a box of volume V. Then a key parameter that will describe how how this granular material behaves is the packing fraction. It's just the physical volume of space occupied by the particles themselves divided by the volume of the box they're in. Sometimes people talk about the free volume, which is just the empty space not occupied by the particles. Okay? Okay, so we have a demonstration here. And there's my granular material. A bunch of particles. These are just sink washers. They are rubber. It's a two-dimensional model here. And they are confined in a box. And as you can see, when the packing fraction is sufficiently small, the particles find places where they're not really touching very much. Well, okay, they're bumping against each other. But they're not touching. There's no forces between any of those particles. And if I were to compress the system by pushing my plunger in, as you see here, I really feel no resistance. The particles just move out of the way and there's no pressure. Until, of course, I push it too hard, and then I can't push any further. I didn't like that end result. This is why I don't like teaching freshman physics. But we can try it again. And I'll push very slowly. Oh, I don't like that either. Well, this shows a problem I'll get to in a few minutes. All right, there we go. That's better. And what do you see there? This state of particles is jammed, meaning that those particles are now locked into the positions by the forces interacting among them. If I were to try and compress it any further, I will feel a pressure in the system, whereas before that there was none. If these were incompressible, I couldn't push this piston in any further at all. If they're compressible, I can push, at a great cost, depending on how strong is the repulsion between those particles. And the other thing that you would really see, and it ain't so well here shown, these particles are not ordered. Okay. And, well, you can see, of course, that they are locally ordered. Here's a nice hexagonal lattice. Here's not. Here's something else. Here's something. So it's a mixture of little regions that are ordered and little regions that are not ordered. But in principle, if I did this in 3 dimensions, which I don't have the nice model for, you would see that when you compress and get to that critical packing fraction, the particles are in some pretty disordered positions. Okay. And so that's the jamming transition. As I have my particles in a box and I compress it, or I add more particles, however you want to get there, as I increase the packing fraction, I go from a state in which the pressure is 0 to a point where there's a pressure that is now finite. Back before this, over here, these particles are in a liquid-like state. If you agitate them, they move very nicely. If I have them under gravity, they flow very nicely. When they're in the jam state, of course, they do none of that, except this guy here. That's what we call a rattler. A rattler is a particle that, because it's missing the right number of contacts, can rattle around in its little cage, but still the structure of the whole isn't going anywhere. Okay? So if I change the focus, you can see that better. Okay.
Steve?
Yes?
What did you not like about the previous 2 considerations?
It looked too ordered to me.
Okay.
And there's a reason why it does, and I'll say that in a minute. Okay. So So the jamming transition is just this transition from a liquid-like state of my grains to a rigid but disordered solid-like state of my grains as the packing fraction increases. And one typically calls that special value of the packing fraction the jamming packing fraction, critical packing fraction. If I have a finite size system, the value of this packing fraction might vary depending upon what my initial state was, but as I let the number of particles get bigger and bigger and bigger, that spread in possible jamming fractions approaches a well-defined number. Okay. Just a few things about that jammed state. Okay, we don't have any thermal equilibrium here, but we do have mechanical equilibrium. And in that jammed state, each particle, except for those isolated rattlers, each particle is in a state of mechanical equilibrium. So if I look at the net force on each particle due to its neighbors that it's in contact with, that sums to zero. And also if I were to try and displace one of those particles a little bit, those forces would push it back to where it was. Yes?
So the jam state is just a result of the initial configuration, not of the...
I'm sorry, say again? The jam state is
a result of the initial configuration, not of the...
Is a result of the initial configuration and not a result of the speed of the compression. Ideally, if this were to be something we could hope to have a theory about, it shouldn't depend on either of those, right? Now, in a finite size system, I says it can depend on the initial configuration, and as the system gets bigger and bigger, it doesn't. The question that you asked, does it depend on the rate of compression? It could, and we have in mind a very slow compression.
Yeah, I mean, like the one you example here.
Yeah, so clearly it will matter, right? But when I'm speaking now, I'm speaking of a very slow compression, and that limit, hopefully, it's well defined. Yes. Numerically, when people try to simulate things, they have their particles in a box, and then they continuously scale down the size of the box and relax the particles always to be at some local energy minimum, so that's like an infinitely slow process. Okay. Okay, so forces balance. And also torques balance. Okay, for disks, you don't really care too much about that, but if these were ellipses or some irregular shaped particles, you would also want the torque on each particle to balance in the jam state. Okay. And you can say the nature of this jam state. For example, what is the value of the packing fraction at which this jamming occurs? And some geometrical properties of the network of contacting particles that are in those jam states. That can depend, to some extent, on a couple of things. So for sure, it depends on the dimensionality of the system. So 2 dimensions, 3 dimensions will have different packing, critical packing fractions. What it also can depend on frictionless versus frictional particles. Okay, so if I have my particles here, they're in contact, there'll be a normal force pushing them away from each other, And if these particles were, infinitely smooth, that's all it would be. The force of contact would always be perpendicular to the surface where the particles touch. But if the particles were rough on their surface, there might be some frictional forces between the particles, as they not just hit like this, but as they slide past each other, and that could give rise to some tangential force like that. And people usually, nobody really understands what friction is, just take the same model for friction that you had in freshman mechanics to say the magnitude of the tangential force at contact has got to be less than or equal to the magnitude of the normal force times some parameter, which is the coefficient of static friction. Okay, so the frictional force can have any value, the magnitude up until the normal force. And okay, so our jam state will depend on whether the particles are frictionless or frictional. And it will depend on whether the particles are spherical or disk-like, as in this example, or whether they are non-spherical. And when they're non-spherical, that's when you have to worry about torque balance and things like that. Okay. Much of the next two lectures, I will concern myself mostly with frictionless spherical particles, which are compressible. But in this lecture, we'll also consider some properties of the more general case. But to start, let's start with that frictionless spherical case. So frictionless spheres. For the case of frictionless spheres, this jamming, let's imagine now frictionless spheres rigid. Okay, so the spheres cannot push into each other. In this case, that state that you get when you jam the system up, okay, and because they're rigid, I can't press them together any further. That state you get when you jam them up is often called the random closed path state, or RC. Okay. And what does that mean? Well, you're just supposed to understand it intuitively from the name, right? Closed path, the particles are touching each other. Yes, question?
I'm a little confused. Is the phi j, is that a unique number?
Phi j is a number that is unique under certain constrained situations. So, if I have a two-dimensional system of spheres, say I take a bidisperse distribution of spheres, and the limit that my system gets infinitely large, and I have a well-defined procedure of how I'm compressing, that phi j for that system will be a unique value. It will be one value if the spheres are frictionless. It might be a different value if the coefficient of friction was something else. But for there are particles with particular properties, that's supposed to be a unique number for that system. Okay, whether it really is, that's a different question. Okay.
Sorry, I think that statement has been disproved already, right? I mean,
Which statement has
this
been
is the statement you made that even for a process that is same for system.
Yes.
I think Torquato showed this, Salvador showed this in a paper.
I'll come
but
to-
It's not unique, right?
I'll come to Torquato later in the talk. Okay? So, yes, Torquato is a big enemy of random close packing. Okay, so what is random close packing? Close packing means I jam those particles right up against each other as tight as they can fit. That's close packing. Random means the positions of the particles are random. Okay, so you, of course, are all familiar with different type of close packing, ordered close packing, right? So you know from your freshman solid-state physics class that in 2D you can have a close-packed hexagonal lattice like that, where the particles are all close-packed, and they are a nice Brownian lattice, they're ordered. In 3D, you have a nice close-packed SCC lattice. So, ACP is another close-packed lattice. And here, the main thing is that these particles are close-packed, but they're ordered. And you can compute what is the packing fraction of these systems. And for the hexagonal lattice in 2D, it's 0.9 something. And for the SEC in 3D, it's 0.74 something. Okay? When we're talking about random close pack, we don't want ordered things like that. We want disordered packings like that. Okay? And the value of the jamming packing fraction in that case, for random packing, is well known for a long time now, both from experiments and numerical simulations, and very consistent within, error bars of doing things. And in 2D, this is about 0.84, 2 dimensions, about 0.64 in 3 dimensions. Okay, so the main thing is...
Another question?
Yes?
So this experimental and theoretical RCP, does that include your quote-unquote isolated rattlers? And what fraction of isolated rattlers does that contain? And
so that's a good question, and I don't know the exact answer. I think the fraction of rattlers one typically finds is about 2% or something like that. And yes, the value of phi in compute includes those particles as being in the system.
Are those numbers entirely numerical, or can you write down some close form for them?
Well, I'm going to write down for you in a minute a simple theory that estimates the value. Yes?
Is this phi RCP at all related to the average of all close packings?
The average of all close packings, no, because I don't think so. Again, let's save that question to when we come back to Torquato.
Quick question.
Yes?
So this experimental figure,
Yes.
I understand that they repeat an ensemble of experiments, they get some
Yes.
distribution,
Yes.
and in principle, this phi can extend beyond that.
The distribution has tails, yes.
Has tails, and this is the...
Well, as the number of particles increases, the width of that distribution decreases, and you believe it approaches a well-defined value. Okay, and that is certainly seen in numerical simulations. Experiments I'm less knowledgeable about, to say this. Okay, but the main point is that the random close packing fraction is, not surprisingly, less than the ordered close packing fractions. Okay, because I'm not optimizing my use of space. Okay, so again, one thing to say, and I'll come back to that there. and this is a little bit relates to the point that was mentioned about Torquato and his objections. You can ask if this is really so well defined, because clearly I can get to higher densities by making an ordered structure. And so you can imagine I can also get densities in between this and the ordered packing fractions just by locally ordering a little bit, and so on. And you can even get jam structures at a phi which is less than random close packing. For example, just think of a honeycomb lattice in 2 dimensions that has a packing fraction lower than 0.84. And it's stable, but that again is ordered. So there's some question about how much order you want to let mix in to this affecting the value of phi j. And that's what I was sort of unhappy about here, because there is quite a lot of local order in there. Okay. Which also brings me to a point I meant to mention. Let's see if it's the next slide. Okay, here's the next slide. When we do this experiment of compressing particles in 3 dimensions, you will often find that even if the particles are identical, the same size spheres, nevertheless, you get a state which is random close packed. Here's a picture of an experiment done in the 50s of compressing ball bearings. And you see, here's a region where they are FCC ordered. Here's a region where they are RCP ordered, and they're happily coexisting. And it's not easy to perturb this system and get it to suddenly order. On the other hand,
the ball bearing.
Question? What?
Disperse of the ball bearing.
Oh, I don't know.
Because I could imagine like 1 or 2% off would really screw it.
Okay, but in numerical simulations, for example, where they are monodispersed,
right? But this is
depot.
Yeah. But
Yes.
You're talking about experiments.
Okay, that's just okay. But in simulations, for example, of monodispersed spheres, they also see if you compress them, you get random packed states, and in fact, that system is one of the standard models of simple glassy materials, and the connection between granite materials and glassy materials we will come back to in the 3rd lecture. Okay, but if I take this 2D system and I perturb it a little bit, well, you can see very quickly it's becoming quite ordered. And so in 2D, if you have monodispersed particles, they can jam in a random state, but if you tickle it a little bit, it's very easy for that state to become ordered. So when one is trying to talk about random close packing in granular materials in 2D, which is certainly a lot nicer to do simulations in 2D than 3D, one often does go to either a bidispersed or a polydispersed system, because if you make the particles not all the same size, then it becomes very hard for them to order, as I hope this demonstration will now show. So I've added a bunch of big disks to that, little disk and big disk, and now we're going to shake them up. And they mix quite nicely, sort of. And now if I compress them, they're disordered. And I can't wiggle them or jiggle them in an easy way and get them to order. Okay? So, when we're going to do simulations later about grand theories of 2D, we're always going to be talking about a bidispersed, and some people do polydispersed systems, to inhibit this ordering of the system into a crystal. Okay. How's the time? Oh, boy. Okay. So, these are such easily reproduced numbers in 2D and 3D. Lots of experiments and lots of simulations come up with them. And so you would think that that's something you should be able to calculate and do a calculation that gives those numbers. And the point is that it's not so easy. And so I'll give you a very simple model in 2D. This is by Williams. It's in PRE. In 1998, the exact reference is in the notes you have. And so the first thing you should note is when this work was done, 1998. So certainly all the lecturers in this summer school could have done this result, right? So what is his model? Let's go to the next slide. That's a picture from his paper. He considers some local cluster of nearest neighbor particles. We're talking about spherical incompressible particles like that. And the way you can determine which particle is a neighbor of which particle is by doing a Voronoi tessellation of this plane. What that means is you take, for example, a line from the center of, say, this particle is the one we're interested in. Take a line from the center of that particle to the center of the other particle. Center of this particle to the center of that particle. Center of this particle to the center of that particle. Center of this particle to the center of any other particles in the system. And then when you draw all those lines, you draw the lines that bisect it. Okay, I can't reach up here, but you see here are the bisecting lines from those three neighbors. And the inner envelope of all those lines is then the set of points which is closest to the origin of this disk than to any other disk. And I could do the same thing for all the particles. And that's a unique tiling of the plane determined by the positions of the particles. We say then that two particles are nearest neighbors if they their Voronoi cells are touching. So in this case, these three are all nearest neighbors of that one. Okay. Once we have that tessellation, we can also do a triangulation like this. So connect the origins of all the disks which are nearest neighbors, and this is a unique triangular tiling of the plane. Okay, and so what William said is, let's look at such a configuration where this angle here is whatever it might like to be. This is a rhombus. All its sides are equal. It's equal to twice the radius of a disk, or the diameter of one disk. And all these angles here are the same. So those are isosceles triangles. And let's consider two cases. If theta was 60 degrees, then these are equilateral triangles. And what I get here is that these particles are in the configurations of hexagonal close pack. If I tried to make 60 theta get bigger than 60, the particles wouldn't fit together. On the other hand, if I decrease theta and take it down to 45 degrees, then these are right triangles like that. And now when I do this Voronoi tessellation, I bisect this line, I get like that. I bisect this line, I get like that. And I bisect the diagonal, and I get like that. And that's no longer contained in the inner envelope of these lines. So below 45 degrees, this particle is no longer a nearest neighbor of that particle. Okay, so if I'm looking for configurations of neighboring particles, I only have to consider angles going from 45 to 60 degrees. And then William says, let's just say that random close packing, what I mean is that these local clusters like this, the angle is equally distributed anywhere from 45 to 60 degrees. Okay, that's the ansatz. And then you can find out what's the packing that would produce. So let's look at some particular cluster like that. And the way I can figure out the packing is just look at one of these triangles and count the fraction of the area in that triangle that's contained by the disks versus the area of the triangle itself. And so here, since the angles of this triangle are 180 degrees, the area of the disk contained in that triangle is just 1/2 the area of the disk. And then I want the area of this triangle, which I'll draw it on its side like this. This is theta, and this is theta, and this is 2r. So this length here is 2r cosine theta, and this height here is 2r sine theta. And so the area is 4r squared sine theta cosine theta, or just 2r squared sine 2 theta. And so we'll divide that by 2r squared sine 2 theta. The r squareds go away. We get pi over 4 sine 2 theta. And now, if theta had to be between 45 degrees and 60 degrees, the typical theta is 52.5 degrees. Right? Just the average. And so if I just stick in here, sine squared twice that is 105 degrees, one gets, what did I do wrong? Sine 2 theta, not sine squared theta. Sine 2 theta. There. That's right. Okay? 0.813. Okay? And now you can say, well, that really was too simple-minded. I should just take this formula and stick in theta bar like that. What I should do is consider this for all theta and then just average over theta from those two limits. And if you do that, it goes up a little bit to 824. And that's not too bad compared to 824, given a model that has almost nothing in it. Okay. Perhaps it has little in it, I don't know. And then, that's in 2D. 3D, this was such a difficult calculation that it took until 2004 for the corresponding calculation to be done. Okay, 2004 Journal of Chemical Physics. So they generalized this kind of calculation. It's not worth seeing the details, but then they found from that calculation 0.6394, which is even better. So, that's random close packing. And now we can come to Torquato, who says, well, random close packing isn't a well-defined mathematical concept because what are you doing? I mean, how do you know it's not different if you do things differently? And so he has proposed a different way of looking at the problem. Okay, I already told you that if I'm willing to accept little bits of ordering into my random packing, I can make that density go up. And so what he proposes is to define some parameter psi that measures how ordered the system is. And then we can draw a phase diagram of this ordering measure versus packing fraction. And this stuff here is not allowed. This stuff here is all liquid. And jam states can all exist over here. The point B is just the SEC ordered close pack. There's some point here A, which is the jam state, which has the lowest possible packing fraction. But as you see, it's not that packing fraction which has the lowest value of the order. And then there is some value, some jam state here, which is jam and has the lowest value of the order, and that he called the maximal random jam state. Okay, so he's covering now all possible ways of constructing all jam lattices, not just how I do it with my plunger, and then defining the maximal random jam state, maximal jam state. And in his numerical simulations, that packing fraction in 3D turns out to be about 1.64. So whether it's really different from random close packing or not, well, it's not clear. Huh?
That's unfair.
Huh?
That's very unfair.
Oh, I don't mean to be unfair. I don't think it
I mean, the point of this whole exercise was to prove that there's no unique state, and it's particularly relevant for both jamming transition and glass transition. That people have been talking about this one unique state, which is configuration, entropy goes to zero. I think that was the point of the exercise, that you cannot have that unique state. So the value is same, doesn't mean anything in this context.
Well, again, the idea is that this is meant to describe a case in which all the particles are random, which in a sense is the same idea as the maximum random J state.
No, but
and if I get,
there are configurations that are very, very close to that, which are also equally accessible.
Yes.
I think that's the difference, right?
Correct. Okay, I will go. But again, the idea that one is looking for a random state and not something else, I'll come back to in a. All right. Okay. We'll see more from Teitel in a minute. Okay, so that's the random closed packing, which, even if it's not mathematically well defined, appears to be reproducible, at least within some range of possible width in many experiments and simulations. Yes?
Sal's calculation was done for mono dispersed perfect.
I believe so. Okay, so now we want to look more at some of the geometry of the jam state. And so we'll discuss what's called isostatic packings. And a jam state which obeys the isostatic condition is sometimes called a marginal state. Okay. So we said that a jam state should be in mechanical equilibrium for each particle except for those few ratas which we will ignore. And that means that the force on each particle should balance to zero. So I can write, let me consider a particular particle I, and the force balance on that would be like this. Fij, J, the sum on J is the sum over all the particles that are in contact with I. Fij is the force on particle I from particle J at the point of contact, and the sum of those forces should sum to zero. All right. We also have torque balance. And I'll write that the following way. The sum on J. Here are two particles in contact, and here they don't have to be spherical. This is particle I, and that's particle J. Dij is the distance from the center of particle I to the contact of particle J. And I guess, let me define Fij like that. The force of particle I on particle J, which is just minus the force of J on I. Okay. And so what I've written down here is the force moment tensor, right? Usually torque is R cross F, but that's something that really only works in 3 dimensions, or 2 if you think it. If you want to go to a general dimension, the cross product of any two vectors is really an anti-symmetric second rank tensor, and we can write it like that. R F minus F R. And so that's the condition of torque balance. And so if I gave you the geometry of my network, so here, for example, the particles all in some particular positions, contacting in some particular ways, I'll know all these D's, and I could then look at this as a set of linear equations for the unknown force variables. And I can try to solve for what they are. That would make that a stable configuration. And we can ask now how many such linear equations are these? Well, if we're in D dimensions, each force vector is a D-dimensional object, has D components. The number of force balance equations is n times d. How many components are here? Well, this is an anti-symmetric second rank tensor. So the number of independent components there are d minus 1 over 2, and again 1 for each particle. So there's so many for torque balance. If you add them up, you get n d plus 1 over 2. Okay, that's how many linear equations there are. So we have and those so many linear equations have so many unknowns, which are the components of the contact forces. And if this number here is bigger than that number there, then there are more equations than there are unknowns, and in general you would not expect to find a solution. So that describes a network which isn't mechanically stable. Okay? On the other hand, if this number here is less than this number here, I have more unknowns than equations, and I can find a whole class of solutions. Okay? When those two numbers are equal, I have just as many equations as unknowns, and then I could solve, presumably for unique forces that make that lattice stable, and so that's only marginally stable state. And the argument goes that if I somehow took a marginally stable state and removed one particle or cut one bond somehow, then the system would have more equations than unknowns, and it would go floppy and soft and become unstable again. So the idea is that this marginal stability is what characterizes the jam state at the jamming transition. Okay? All right. So let's
would the reverse be true? Nowhere in the system is there space to stick a single part.
Yeah. Well, if they're compressible, I can always jam it in.
Yeah.
And if they're not, well, then I can never get beyond the random close packed density and still have everything which is everything random. Okay. So let me make one statement about randomness here, not randomness. This kind of argument that I'm doing here assumes that all these linear equations are linearly independent of one another. Okay? Because if they're not, then I don't really have as many equations as I thought. And that's what you get if you're constructing an ordered closed packing. All those equations are really dependent upon each other. So that's again where the idea that these particles are random comes in, the assumption that these equations are not linearly dependent. They're all independent of one another. And that's only if the particles are all suitably random. Okay. So a key parameter that would describe the geometry of my jam state is the contact number, Z. How many particles, and if this is grain I, how many other particles grain I in contact with? And then averaging over my marginal state, I can compute the average contact number. Okay. And so when I have an average contact number that's just the right amount, that my unknown force variables is exactly equal to the number of linear equations due to force and torque balance, we say that is the isostatic value of the contact number, called Z iso. And that describes this marginally stable state, which describes the state just at the jamming transition. Okay, so what we want to do now, I think I'm done here. Just try to calculate Z iso quickly in some special cases. Oops. Let's imagine that these particles are really frictional. They're as frictional as could possibly be. The coefficient of friction is infinity, which basically means that there's no constraint at all on the magnitude of the tangential force. Right? Mu is infinity. It doesn't matter what the normal force is. Tangential force could be anything at all. In this case, all the d components of the contact force and d dimensions are all independent of one another. And so for each contact, I have d unknowns, and the average number of contacts is going to be z n over 2. That's the average number of contacts, because each contact is shared by two particles. That's 2. And then I should multiply by d. That's the number of unknowns, and that should equal n d plus 1 over 2, the number of linear equations. And so we can cancel. And for perfectly frictional particles, the average contact number is just 1 plus the dimension of the system. Okay. And now we can look at another extreme limit. Mu is 0, frictionless particles. So here, no matter what is the normal force, the tangential force is always 0. Let's first specialize to the case of spherical particles. So here's two particles, and that's here's what I call Vij, and then the normal force is always in the same direction. So right away, if you have tangential forces, spherical particles, there's no tangential force. The moment the torque from any particular contact is always 0. We don't have to worry at all about rotational degrees of freedom or torque balance or anything like that. Moreover, each contact force is in a uniquely specified direction, the direction normal to the surface of the contact. So those contact forces have only one independent component. And so now if I want to equate, I get the number of contacts is that right? Times z, yes. No, that's right. That's the number of contacts, And since each force is only one independent component, that's the number of unknown force components. And that should equal the number of linear equations. And the number of linear equations are just the equations from force balance, because we're not worried about torque balance anymore. And so that's ND. Okay, and so this then gives ends Z iso is 2. Okay, so for frictional particles of any shape, the isostatic contact number is D plus 1. For frictionless spheres, the isostatic contact number is 2D. And if I have spheres with some finite coefficient of friction, then one expects that the isostatic, or it's not right to call it isostatic, but the average contact number is between those two limits. Okay, so friction certainly complicates things and makes it more systemically clear. Okay. I see I'm running out of time. We've got 2 more things to say. This was frictional spheres. What about other shapes? We can have 2D. We can have discs and ellipses. In 3D, we have spheres. We can have spheroids. And we can have ellipsoids. By spheroid, I mean an ellipsoid which 2 of the axes are, or 2 of the principal radii are equal. An ellipsoid, all 3 are not equal. And what I can do is take a similar kind of argument, except now I have to consider the torque balance in those directions around which the object is not symmetric. And so I can write the same equation where instead of just D for the D translational degrees of freedom, I'll write dF for just the number of independent degrees of freedom of each particle. So for a disk in 2D, that's 2 for translational. An ellipsoid has 2 translational and rotational, 3. Spheres in 3D is 3. Spheroids would be 5. Ellipsoids would be 6. And so for such a frictionless object like here, you might expect the isostatic packing to be given by twice these numbers. And that would describe jamming. Only there's a problem. Why it really can't do that. Right? Because take a sphere, which would have its marginal state at jamming when the average Z was equal to 6. And now imagine just distorting it a little bit. Not a lot, just a little bit. Well, immediately, no matter how little you distort it, it becomes an ellipsoid. And Z should then go up to 12. And so you would expect something discontinuous to happen, which clearly doesn't really happen. And so, again, not claiming to understand the calculation, but Torquato then came to the rescue here in doing calculations and simulations for various shaped objects, show that, in fact, the isostatic condition doesn't generally work unless the object is sphere. And so, if you look here at the jamming density here versus the aspect ratio, well, okay, let's look here first. Contact number versus aspect ratio. Down here are spheres, and then they become more, I forget, this one here is for ellipsoid, and this one here is a spheroid. And you see, for low aspect ratios, the average contact number increases smoothly from its spherical value, and it's only as the shape gets rather elongated that it doesn't even quite reach this isostatic value. If you look at the jamming density starts at the value of spheres, 0.64, goes up as I increase the aspect ratio, and comes back down again. Okay? And so
Is there a simple way to understand why there's that maximum and where the maximum should be?
As I was just going to say, I have no simple way to understand it because I haven't read the paper and studied it, but as a non-expert, I can do that. But this is the paper to read. Okay, it's again very nice. Okay, so isostatic condition seems to work very well for spheres, frictionless and frictional, but you have to worry when you get to things that aren't spheres. And so now one last thing to show, again, just another result that I can't say I can prove to you offhand. But now let's look at spheres, okay, in 3 dimensions. And these spheres may have any value of friction from u equals 0 to u equals infinity. And then again, a nice paper by Maxi in Nature. He proposes the following diagram that tells me as a function of packing fraction what should be the average contact number at jamming. And so this line down here is just the value d plus 1 for perfectly frictional states here. This point here for 6 is just the random close pack for frictionless. All these different curves correspond to another parameter of the ensemble called the compactivity, which hopefully I'll say something about in the next lecture. But as you go from mu equal infinity down here to mu equals 0, you flow on all these curves from down here at 4 up to 6. And this line here is the random close pack line. And this line here represents for all ways of preparing the ensemble, what's the smallest packing density you could get for a given value of the friction. And the given value of the friction sets on the average contact number. So that's this line here, and that line brings in another piece of terminology, random loose packing. Okay? So random close packing is when the particles are frictionless, and you stuff them together, and you see they jam at a certain density. But if they are frictional, as we said, they can pack at a smaller value of the contact number, d plus 1 rather than 2d. And if the average contact number is smaller, you should expect that the average packing fraction is also smaller. And so frictional particles will in general pack at a packing, or jam rather, at a packing fraction smaller than random close pack, and that smaller value is sometimes called random loose packing. And then I could squish them together and get their density up all the way up to random close packing. Squeezing. Right? So I think with that, I will end.
Great, thank you very much. Questions?
Can I ask why you would expect the average contact number to be smaller when mu is not infinite? Because I thought it was all due to the fact that you've got more linearly independent equations. So even when mu is not infinite, you would have the same number of independent equations.
The question, I'm supposed to repeat the question. The question is, why do I expect the packing fraction to decrease when mu is bigger than 0? Was that the question? Say it again.
But you said that, so Z iso is equal to d plus 1 when mu is infinite.
Yes.
And you wrote there that when mu is not infinite.
Mu is
but when it's
0 there, in general it's in between. Yes.
Why would you expect that it's in between when mu is finite but not infinite?
Wait, Z?
No.
As mu increases from 0, Z smoothly decreases from its maximum value to its minimum value.
Why would you expect that?
Because the tangential forces can help stabilize the system. I mean, I had extra forces to hold things together.
But the way you divide Z iso to be d plus 1 is based on the argument that you've got a number of linearly independent force equations.
Yes.
So when mu, let's say, is 10,
Yes.
Wouldn't you have the same number of linearly independent equations?
But the number of the components of the force is not necessarily d, because the tangential force cannot be anything it wants to be. It's bounded by the normal force as a maximum. So it's not d-independent components. There's some relationship in terms of bound between the tangential force and the normal force. So this statement is not true anymore. The number of equations is somehow, I guess, less than d, somehow. And if I do that, I don't know. Does it work the right way? I hope so.
I guess my question is, whenever some of the coefficients in your linear equation is non-zero, then by your argument about the randomness of those coefficients, you would expect them to be linearly independent.
I would expect the equations to be linearly independent.
So I guess
the statement whether the equations are linearly independent or not has nothing to do with the forces being frictional or not. It just has to do with where the particles are. Right? Those force and torque balance equations have the Fij as unknown parameters. The friction comes into play when you want to consider how many of the components of that force are really independent unknowns versus how many are dependent upon other of the components of the force. And so the extreme limit of mu is infinity when all the components are completely independent, and so there's d of them because the tangential force can be anything you like. And when mu is zero, all those components except the normal one have to be zero. So there's not d, there's just one. And when there's mu finite, that tangential force can be there, but it's bounded by the normal force. So there's some constraint, which is not necessarily easy to put in any analytical description, at least not for me now. And so,
it has to pack better for finite mu simply because some tangential force will exceed mu Fn, and therefore that's not a state that's going to have to relax from.
Pack better than what?
That you start with one where the mu is infinity, then it's going to jam, and then if you make mu finite,
yes, some of those contacts will go unstable,
which means it has to relax to some denser state.
Yes.
For the isostatic case, when you showed the data for the the other paper which I don't know, so that was done exactly at the isostatic condition. I mean, like
no, this is not. This is done simulating particles and using some protocol for compressing the system and determining the packing fraction at which the system jams.
I see. So it's not isostatic, right? So the jump is only a.
So what I'm saying is, what the point of this paper is to show that the jamming packing fraction for non-spherical particles is not described by the isostatic condition. So the average contact number here, if isostaticity held, it would have only, say for spheroids, two numbers, 6 or 10.
No, wait,
and anything, there wouldn't be anything in between. Maybe I'm missing.
But isostatic is the critical case.
No. Isostatic.
It is actually, right? I mean, it's just barely.
Well, okay, maybe it's a definition. What I'm saying is, as I understand it, the isostatic condition is defined to be when the average contact number gives the number of degrees of freedom, and the forces is equal to the number of linear equations. That's the definition of Z isostatic.
Yeah, so
and let's just then is a question of whether that packing fraction which does that is the same as the jamming packing fraction as determined by some simulation on the real or experiment on the real system. And the claim is it is if they're spheres, and it's not necessarily if they're not.
No, this is very confusing. So if you start from a system and you do any jamming transitions, basic experiment, like you just increase the packing fraction.
Right.
When you reach the isostatic condition, when that is fulfilled, your system is just jammed. If you move one particle, the system is not jammed anymore.
Well, no. Okay, that's the point of this paper. That's not so. That you can jam when the average contact number is smaller than the isostatic value. So when I have spheroids, which have an aspect ratio which isn't too big. When they jam, say aspect ratio, whatever that number is here, their average contact number will be 9 rather than 10. So it's hypostatic is what happens at jamming. And why this argument that I gave you here fails, as I said, I don't know yet, but if you read this paper, they give some physical arguments as well as a calculation to show itself. And the point that this isostatic counting argument really only can be applied to spheres was apparently known earlier than this paper. So it's just not generally appreciated. So, yes?
A question along these lines that I think maybe the answer resolves the conflict. Are the packings, the hypostatic ellipse packings, mechanically stable?
Yes.
They are mechanically stable?
Yes.
So irrelevant with, with respect to how I get there or whether or not I've satisfied isostatic, they are jam packings.
Well, I mean, yes. So in the simulations, you just start from several different initial conditions, and do this compression, and get your jamming density, and average that over as many configurations, and that's what this curve is.
And within the context of Torquato's work,
yes,
this paper, how do I know that they're mechanically stable?
Oh, because he tells you what he
tells
is.
you, okay.
He's a serious guy.
Suppose that the system is a little different from the marginal state. I mean, suppose the condition is goes a little away from the marginal state. So in this case, it is possible to do some differential series.
I don't know. If you're at a packing fraction above the isostatic value, then you have many solutions for the forces that would make that network rigid, and that leads to something that's known as the force ensemble for describing that packing above jamming. One assumes that all possible force solutions are equally likely, and then one can compute things and do things. But I don't know about what you're saying. If that's really a critical point in some sense, perturbation theory might not be working very well. Yeah, I don't.
Is that a quick question?
Yeah. So when you are talking about going between the DFs here, like you have in like the little table thing.
This.
Yeah.
Yes.
So you're saying, consider a spheroid, and then I pinch it so that it's not anymore, and it's an ellipsoid, right? And you're saying if you do these sort of minor changes, you don't really expect drastic changes in the system.
Right.
But I mean, for that to be true, wouldn't you have to do it to every particle in the system simultaneously, which is a pretty big change? So maybe you would not expect. I mean, maybe you would. Maybe you're not so surprised that it's such a.
Again, all I can say as a non-expert is I haven't read the paper in depth to answer these questions. But it's apparently the case. It has to do with really understanding the effect of the shape of the particle on how it locks in. As I'm talking, I'm recalling something. These conditions of torque and force balance are sort of a linear stability condition, and it turns out that we should really go beyond that to a nonlinear next term, and I think that can stabilize the state of the particles on the sphere. That's the best I recall of what the argument was. But again, look at the paper because I trust them. And there are experiments on M&Ms which prove this also.
Okay, so thank you again, Steve. Together again tomorrow morning at 9 a.m. for the second part of